Okay, so good evening once again. We had already started with generative models last time, and I kind of was rushing through because we were out of time. But I'll just do a quick recap. There are three main types of generative models which we have looked at: autoencoders, GANs, which are the generator, discriminator, um, generative adversarial networks, right? And then the diffusion models. So these are basically models that are used to generate new content. And we have the ones that we use simple generational models or generative models rather that we use for text generation. Or when you now go to more complex kind of data generation, like images, like music, and a bunch of other things, then you now see that there's a bit more uh, involved designs. So just going through it, right? A generative model is a model that's designed to create new data. So I think that's kind of what we've talked about. It creates new data, and it creates new data because it has learned patterns and distributions of the training data, right? And it applies those. So essentially, it has what we call the latent knowledge or the latent representation or representative knowledge, right? It has an internal representation of the knowledge it has extracted from the data that you've trained it on, right? So with that internal latent knowledge, it is able to generate um, new things in the same shape and form as the original data it was given, or maybe similar to the original data that it was given, right? So they learn underlying data distribution and use that to generate new samples. Of course, there are many applications of these. So you see image synthesis, text generation, which is what large language models are doing, basically the GPTs. Then you have audio and music generation, data augmentation. So data augmentation is you have some data already, you want to generate similar data. This is typically, of course, used for training neural networks. So they can generate their own data that would be used to train. In fact, we did an example of that, of course, last week, where I showed you how this same principle can be used to train a model to play a game. So the model, you give it the rules of the game, it plays against itself, right? And then it makes mistakes. You also deliberately introduce the mistakes deliberately so that it can learn new things. Over time, after training for a while, it begins to learn the patterns in the game, right? And it is generating, so in the process of playing the game, it is generating data for itself that it will use to train itself, right? And so you can consider that as data generation or data augmentation, right? Then representation learning. Representation learning is basically um, where you train a model and it learns a particular representation of the data that you have given that model to train. And most times it will learn um, a more efficient representation of that data, right? In fact, sometimes it's used for compression and things like that. So in generative models, instead of predicting labels, right, they generate um, basically the next item in a sequence, or they generate something similar to what you gave it in the training data. So that's generative models. These discriminative models are the ones that learn to predict, a label or a classification. So effectively, with generative models, with discriminative models, you are learning a decision boundary, which is, for classification. While with a generative model, you are learning the full data distribution, right? So that you can generate new data that fits into that same distribution. That's basically what that is. So discriminative is learning a probability of y given x, while in generative is just learning the probability of x, right? Uh, discriminative is used for classification, while generative is used for data synthesis. Discriminative is used for logistic regression, while generative is used for um, a bunch of things. These are the models that I used. So I also talked about this where in representation learning, you are basically taking data from a particular space and use an encoder to train on that data, and it comes up with a latent representation, an internal representation of that data, right? That's representation learning. While in generative modeling, you use that representation space and use a generator or a decoder. It's actually a decoder, right? That will now generate sequences or generate content that kind of um, represents that internal meaning. So we also talked about objectives in generative modeling, right? You have three different kinds. This is kind of a new method that was being considered flow-based generative models. But we have GANs and variational auto encoders as like two of the main methods that are currently used for generative models, particularly in image generation, right? So we'll look at these two main approaches and the difference between them. But you see that in all of them, you can model them as um, the initial sequence coming in, the training data coming in, right? Through an encoder, and then you have an internal representation that then goes through a decoder. But in a GAN, right, they are actually two different models. So you cannot say it's a single model. They're actually two different models. You have the generator model and discriminator model. So this is a discriminator model, which actually takes the generated input from the generator model and does a prediction basically. So this is converting to latest space and does a prediction or a classification to say whether this input matches the real input. In other words, whether it's good enough to pass for the real thing, right? So that's basically what it's doing, comparing the generated input with the real input. And then when it compares, so this comparison is external to the generator. That's the main thing with the GAN. Right. So GAN has two models. You have to train two different neural networks. And this is one of the biggest challenges with GAN when we talk about it later on. The fact that you're training two models, it takes a lot of time. But the generator is again a decoder. So it has its own internal representation, which it is learning. And it learns this internal representation by trying to generate an output that it increasingly becomes closer and closer to the real output, to a point that the discriminator cannot differentiate between its own generated output and the real output, right? So you give them two objectives and they're fighting against each other, basically. So it's like saying the generator is generating more and more images that look like real images. The discriminator is learning to become better and better able to discriminate, right? To distinguish between the image generated by a generator and a real image. So it is kind of a feedback cycle. As the generator is getting better at it, the discriminator has to also get better. And so they both get better and better in a cyclic loop. And as they get better and better, you know, they have to get better because as the generator is getting better, it's like putting two people like a penalty taker in football and the goalkeeper, right? The goalkeeper gets better at catching the balls. The penalty taker has to get better at kicking the balls. But as the penalty taker gets better at kicking the balls, then the goalkeeper also has to get better at stopping the balls. So they kind of end up training each other, in a feedback loop, and each becomes better and better. So at the end of the day, yes, you come away with a generator. It's really a generator that you want at the end of the day. But this is kind of an old method these days, right? We hardly see GANs. GANs were overtaken by variational autoencoders and the diffusion models. So in the variational autoencoder, first of all, we'll talk about an autoencoder. An autoencoder is basically an encoder that trains itself and it learns the latent space, right? And how it learns is that it has a decoder attached to it. The decoder generates the output again. And you now take the output that the decoder generates and compare it with the original input. And that generates a loss function. And back propagation is applied, backwards across it. So the main difference there is that the loss function is and the back propagation, the training is done internally. So the autoencoder is a single entity, it's a single network, right? It's not like again, there's actually two networks that are fighting against each other, but the autoencoder is a single network that basically learns from itself. That's why it's called an autoencoder. It learns to encode by itself. It's an unsupervised network, basically. It trains on data you give it. You don't need to give it labels. It takes the data you give to it. It trains itself to replicate that same data, and it gets better and better, right? So let's move on. Um, so let's talk more. I think I've kind of explained autoencoders already. Autoencoder basically is used to learn efficient encodings or representations of unlabeled data. So it's unsupervised, like I've said. It learns two functions. So it's first of all it learns both at the same time. So when I say first of all, not like it first of all masters being an encoder and then it learns being a decoder, right? It does both at the same time. So you have the encoder and you have the decoder, right? So it learns the encoding function that transform the data, in the data space into its own internal latent representation of that data. And then from that internal latent representation, the decoder also generates data, and you compare this data generated by the decoder back, against the data generated by the data that was used to train the encoder. So it essentially trains itself by comparing what it had generated against the original data. And that's why the loss function is this, right? The loss function is basically x minus x hat. So you see that there's nothing like y hat. Y hat would be if you gave it label data. But x hat is the same data that you are giving it as input. It has to generate it again. So this is basically mean square loss. Remember, it's x minus x hat squared. This is L2, right? Norm. And you calculate that, that's the loss function. So that's how an autoencoder works. Now, so this is a good example. You can see it's a very simple case. You can see the encoder here, right? And like I said, you could see that the input dimension is 784, right? Channels, while the latent dimension, which is how it represents data, is 32. So you are training it to compress into a more compact representation of data. And then the decoder essentially does the opposite, right? It takes data in that latent dimension, which is 32, and it generates the output, which is 784, right? Of course, the sigmoid is now used to kind of, let's say you are using you need the sigmoid to essentially give you binary zeros and ones. And that is because the input is going to come in as zeros and ones as well, right? The input will come encoded as a one hot. So you now use this to also generate a one hot. But you could also decide to do a probability distribution, right? And yeah, so that's it basically. So you take the X, you put it into encoder, you get the Z, and then the Z goes into the decoder, you get the output, which is supposed to be its own generated output. And this is just a good representation of it. So the auto encoder is going to learn to do what we call dimensionality reduction. So you remember in the classical machine learning, we talked about ways for dimensionality reduction. We talked about PCA and the rest of them, right? Principal component analysis, right? And a bunch of other ways to just reduce dimension. So if you had a 200 and something dimension tensor, you reduce it to just 3 dimensions so that you are able to display it. But the difference between using PCA and an autoencoder is that with PCA, you actually, there's a bit of learning as well, right? There's a bit of recalculation of the weights or the values of those three remaining dimensions. So in a way, it's not total data. You're not losing all the data from the other dimensions when you drop those dimensions. Okay, but here it actually learns a lot. So it's able to do feature extraction, right? And compress those feature extraction features into a smaller latent space. Then it does denoising. So if you train it with noisy, inputs, it eventually learns the signal because the noise will cancel out. If you give it different, like for example, and this is where it's very useful. If you give it a lot of eights, with some of them looking different, some of them having spots and all of that, it eventually learns what is common to all of them. So even when you give it an eight that is noisy, it is still going to generate a clean eight, not a noisy one, because um, it has learned the representation of the signal, not the noise. So when it is regenerating, it will not generate the noise. And that's why it's very, very useful for denoising, right? So these are some of the limitations, right? Because autoencoders basically um they cannot rely they are kind of focused on what we call a point space. So it's not a distribution because of how it's implemented here. You can see we're using a sigmoid, right? So it's not using probability distributions. So in a way, it's limited, right, to how we can sample new data and how we can reconstruct. Um, so in order to solve this problem, we now have the variational autoencoders, right? So in variational autoencoders, you're not just training it with the mean square loss, right, which was the thing. You train it with a combination of two losses. You train it with a reconstruction loss, and then you train it with a Kullback-Leibler um, divergence, scale divergence. The scale divergence is a measure of the difference between two distributions, right? Two data distributions. So I think I explained that already. So instead of mapping the input to a single point in the latent space, right, where you would have said, okay, I map a single point, a single sequence is mapped to a single point in the latent space. Another single sequence is mapped to another single point in the latent space. So when I say single point, let's say your latent space is maybe 32 um, is the dimension is 32, right? So that means you could represent it by 32 numbers, floating point numbers, right? 0 0.1, 0 0.5, and so on. So there are 32 numbers here, right? Basically, that's what it means when we say it's a 32, um, it's 32, the dimension of the latent space 32, right? But the original data had maybe 750 something numbers, basically representing whatever letters, pixels, whatever it is that those represent. You squeeze it into 32, right? But this represents a single point in the latent space, right? A single vector. And that's a weakness of using just a regular autoencoder. But with variational autoencoder, you are now outputting a distribution, right? So it's not a single number here, but a distribution, which is a list of numbers. So you now have a list of numbers, right? So that results in a latent space that is more continuous and smooth, right? So it enables better sampling. Um, we don't have a lot of examples for this, right? I don't have so much time, but we can do a bit more study on this. So you have a total loss, which is the reconstruction loss plus the KL divergence loss, right? And the KL divergence term is what regularizes the latent space. So regularization, remember, is what we use for to prevent overfitting. So it helps with that. Okay, so yeah, one other thing that we talked about is when you're training variational autoencoders, because there is a random sampling aspect, right? Because the way this works is that um you 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 do a bit of random sampling, right? Because when you are taking the input, right, in a standard um variational VAE, the encoder is predicting parameters of a distribution. So it's trying to predict like the mean and standard deviation. Okay. So what happens is that from that standard deviation distribution rather, the model will sample randomly you know, a value from that distribution. Okay. So um it will sample randomly multiple values. Okay. That's how you train it. For each data point, you are randomly sampling, right? So the problem is that that random sampling is a stochastic process, right? It is stochastic means it is non-deterministic. Stochastic simply means it is random. That's what stochastic means. And because it is random, you cannot calculate a gradient. Random numbers do not have gradients. Any function that is random doesn't have a gradient. It's random, right? So you cannot calculate a gradient. And because you cannot calculate a gradient, you cannot calculate backpropagation updates, right? Because the updates to parameters when you're doing backpropagation and training the model is based on the gradient. So what that means is that you cannot train those models. Well, you can train them, but it's not very straightforward. You train the decoder parts, then you train the encoder parts separately, right? That doesn't allow end-to-end training, which is what is like the best approach to training models like the sequence-to-sequence models like this, right? Encoder, decoder. You want to take the output from the decoder and calculate the gradients and go all the way backwards from the decoder through the latent space back all the way to the input, the encoder, to calculate and do all the parameter updates, right? So, but the problem is that this random sampling would not allow it because you cannot get gradient. So this reparameterization trick is just a way to get around it. And the way to solve it is um, you separate that random sampling into two components, the deterministic component and the stochastic component. So the deterministic component of that random sampling function, basically, think of it like a function because that's what it is. It's a function that generates random numbers or randomly samples, but you cannot differentiate it. So you cannot calculate the gradient. It's non-differentiable. But if you take that function and you separate it into two components, right? The first component is a deterministic component, which picks the base value from a normal distribution or a Gaussian distribution is the same thing as normal distribution. That's typically a distribution that, for those of us who have done a bit of maths, you call it the bell curve and all of that. So, so you pick a value, Z, right, from that bell curve. If you pick a value, um, if you remember this thing, for those who did a bit of that mathematics, you remember that. So if you pick a value from this, a Z value, so typically, you would have X here, right? This, um, this is the X, right? So you pick an X here. While this, you can consider this as a Z, right? Um, so let me just sketch it. Okay. So this is Z, okay, and this is X. So you are now sampling a value from this. Well, it should actually be on the body of the curve, but it could also be inside because, well, you're talking about probability distribution. So when you sample a value, right? Let's use this. So when you sample a value, okay, this is now the deterministic part of that random um, number that you use for training or that random data. Then on top of this, you now add another element, right? So you add some extra value on top of this, right? Right. That extra value you are adding is the stochastic component plus epsilon, right? It's actually plus sigma epsilon to be very specific. The sigma is, of course, the standard deviation. So you take Z, which is mu, which is like the mu, which is the average, right? And sigma is the standard deviation, mean standard deviation. But you modulate the standard deviation by this epsilon, which is the random component. So we can now consider this random component. So with that, this value is actually here, right? So if I pick from the same point again, the next time the random component might be a bit less, right? So it might be here. The next time the random component might actually be lower, right? Or might be negative, in which case the value will be down here. And the next time I might actually pick it from here, right? And the random component I'm that, yeah, we can ignore this random component when you're doing the differentiation and just differentiate this because maybe over time the randomness cancels out. So its impact may not be that much. But we will now differentiate only this deterministic part of the sampling. And that is the new part of it. So it's easy for you to say, okay, let's ignore this, right? And just to differentiate the mean, which is easier. So mu and sigma are now external to the random sampling. So you can treat them as normal nodes in the computational graph. You can differentiate them. The gradients can flow through mu and sigma to the encoder when you have actually done the actual um, gradient function of this, right? So that's the reparameterization trick. Okay. So this is just an example of it in code. You will see that when we are calculating it, we have FC1, which is the linear layer, right? Because you're doing a variational autoencoder, so you have a linear layer. Remember we said the variational autoencoder is basically this. Let me draw it here again and put it in the context of this. So it's basically this. You have encoder that inputs into the latent space, right? And then you have the latent space. So let's say the input goes like this. Then you have the latent space. Then you have the decoder that will decode the latent space. And then you have the output sequence, which is compared with the, um, so this is the latent space. And of course, this is the decoder, right? So the decoder is going to um, again expand it because the latent space is smaller in dimension. So it's going to expand it into a larger dimension, which is the output. And of course, we will then take this output, right? We'll calculate the cost function. So the cost function is calculated by subtracting, calculating the difference between x epsilon, sorry, x hat x hat, which is the predicted x and the actual x, right? So you do the cost function. And remember, we said the cost function, um, we are using the Kullback-Leibler KL um, divergence loss plus the reconstruction loss. So, um, so with this, you can see that you have the linear layer, which is the input dimension. So you have this input dimension and goes to a kind of hidden layer, right? That's 400. Then you have another linear layer from the hidden layer to the latent dimension. But in this case, you see that we have FC mu. So the FC mu is, we're still going to the latent dimension, right? It's still going to the latent dimension. So effectively, what has happened is you have two operations in parallel, right? You have two layers that are running in parallel. You have the FC mu, which is this is the deterministic part of it. So you have a layer that does the deterministic part, the sampling, deterministic part sampling. And then you have another layer here that does the random stochastic sampling, right? You can see that they have both the same input size, and the output is the latent dimension. So think of it this way. We now have a second layer here, right? And this second layer is taking the same input as this, right? And it contributes its output into the latent space here, which the decoder takes up, right? But this one is the you know, this is the deterministic aspect, which you can see here, this deterministic aspect, which is basically it exponent value, right? Exponent to a particular logarithm value, right? So this logarithm value can be um, provided. So it's going to be something like, in this case, where it can be anything, right? But we are doing e raised to power um, 0.5, right, times this log var, whatever it is, right? It's a constant which you pass in. So that is the deterministic part. While this other one just samples through that, um, you now have a sampling through that based on this standard deviation, right, which we have calculated. We now do a random sampling, and that is the EPS part here. So you have EPS, okay. So those two will then be added up. Okay. So that's basically what that is. So you're going to get mu plus EPS times the standard deviation. Okay. Um, let's move on. So all of this math eventually ends up, we'll see the end result. This is comparing an autoencoder versus a variational autoencoder. It's basically what we've been saying. Latent space is in autoencoder is deterministic. In variational autoencoder is probabilistic. Because you're not training on a single sample, you're taking random samples around the mean. Sampling is weak. Here, sampling is strong. Output sharpness is sharper, right? Because again, when you sample, you're training it, you're mapping to a single point in space. Here is blurrier. The theoretical basis for this is reconstruction, while here it's a variational inference. Target point latent vector. So it's a single latent vector, a single point, single latent vector in the latent space. That's the target that it learns. But in variational autoencoder, it actually learns a distribution, which is a number of points, a number of latent vectors in the latent space, right? So because you have a number, so think about it this way. Think about it like I am learning to predict a single number versus I'm learning to predict a probability distribution in a classification problem. You're always going to be more likely to get a correct value if you are learning to predict a probability distribution, right? So let me see how I can use that analogy. So here you are learning a single number. Like I want to predict what if they ask you train a model to predict the cost of a house. And the training data you give it is 10, right? The training target. Forget the X, right? The X can be anything, okay? But I want to train it to predict a value, and the value I'm giving it to predict is 10, okay? It is very highly possible that this model um, can predict 9.5, 9.8, 7 point, or even predict 3, right? It won't get this exact value 10, okay? So this is a regression. Think of it like, okay, you're training to predict a single point. It is likely is either you hit or you miss. Okay, you hit or you miss. And if you miss, you have missed. Even if you miss by 0.1 and it predicted 10.1, but your code is looking for 10, so it's going to fail. But that is um, different from in a probability distribution, I give it a one hot vector. So instead of giving it a single value, I give it a number of values, right? I say, okay, instead of predicting number 10, I want you to predict the probability that this thing will be in position 10. So I'm going to have 10 positions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And I want you to predict the probability that what is coming out of the output is going to be in position 10. So each of these will have its own separate probability, right? So I could maybe say, okay, I have this probability for one. I have this probability for two. I have this probability for three, four, like that. So in this situation, you're actually less likely to make a mistake because it will definitely predict this entire distribution. And then all you need to now do is to pick which one has the highest value. And it's likely that you are going to be. So think of this more like a classification problem, right? But it's a multi-class category classification problem, right? A multi-class categorical classification problem. You're essentially saying predict uh, the probability that it is 10. So when you say predict the probability as 10, it's not going to predict only the probability of 10. It's also going to predict the probability of all these other ones, right? And then because of the fact you are sampling randomly, right? You are sampling randomly, it is actually going to learn to predict with a higher probability, the correct number 10. So you're not asking it to predict 10 exactly, or rather you're asking it to predict the probability that it is a 10. That is the difference between predicting a single point in space and predicting a distribution. So distribution is always going to be more less likely to be wrong. Think of it like difference between a classification problem and a regression problem. So that's variational autoencoders. We'll talk a little bit about GANs, right? I won't go too much into it because first of all, it's really difficult to train it. You are training basically two neural networks, um, two weights, the discriminator weight and the generator weight. But it's also been kind of overtaken by better models. But anyway, GANs are essentially two neural networks that you are training to compete against each other to generate more authentic new data from a given training data set. So you give a training data set to the generator, and then the generator learns, to generate data from it. So the generator is effectively a sequence model, right? So when it learns to generate a sequence, that sequence goes to the discriminator. But you could also use not a sequence, but a latent representation. Okay, that could be another thing you could do, right? So if you use a latent representation, um, you don't have to train encoder decoder because if you're using a sequence model, right, it is going to be encoder to decoder. So that is even going to be more difficult to train. So instead, you can effectively just let the generator learn, generate an a latent representation of this input data, right? When it learns the latent representation, the discriminator is going to then take this, um, well, in this case, right, from this drawing, you can see that it is actually real data. So the generator is actually generating real data, not a latent representation. But internally, it's going to have a latent representation. So it's generating real data, encoder, decoder, right? Um, and then oh, it's compares with the sample data. Okay. The discriminator is going to take this real data and compare with the generated sample data, and then it's going to generate an output. The output is going to be how close. It's a classification thing too. How close is this generated sample to the real data, right? Um, yeah. So based on how close, if the this value is then used to fine-tune the generator's output, right? And the generator becomes better and better at generating because as it is, if this has a higher value, then basically this is used to, the gradient is going to be higher. So the changes to the parameters in here will be higher. And it's going to essentially change its generated samples more. And as it matches this more, this difference is also going to become less. So if it becomes less, it will change its output less. So it's kind of, think of it like the same thing that we do with backpropagation. Now, we start out with a latent random variable, which is what we start off with. It takes this latent random variable to essentially generate the output. So the goal is for the generator to learn the underlying data distribution and um, learn the probability, the P of X given X. So essentially it learns to generate. So it's actually learning P of X or it's learning P of X given Z. So like I said, it's either learning it's sequence to sequence where it's learning to generate output given an input. That input can be either the original data you are training it on or some random latent representation, right? So over time, it learns to actually be able to generate the correct output because the discriminator continues to adjust it. And then, of course, the discriminator also learns from this feedback. That's why this comes back here. So if the discriminator, its ability to discern the difference reduces, its own gradient is going to increase. So the discriminator's gradient is kind of the inverse of this it's the value of this loss that it's able to determine. Think of it like a loss or the difference, right? If the discriminator is able to find a large difference, then its gradient will be smaller. So it won't be trained, it will not change as much. But if it finds a small difference, its gradient will be larger, so the discriminator will adjust to be able to find more differences. And that's essentially the method of GANs. So yeah, it's applied for image synthesis, it's applied for text generation, basically the same thing you would say for all generative models, data augmentation, representation learning. So this is kind of a summary of this whole explanation. You have a generator G that takes in the Z, which is the latent representation, a latent random variable, right? And generates a sequence or an output sample. In this case, not necessarily a sequence. I keep using sequence because we talked about all of these sequence models, but it can also generate something that is an image is not a sequence, it's just data, right, in a particular shape and format. Same thing with text. Text is more of a sequence, right? Music generation is also a sequence. But in general, it generates data that has the same distribution. Now, the discriminator is going to take the X, which is the real data, right, as well as the generated data from the generator, and it is going to calculate the difference, what it has detected as a difference. So the objective function you're trying to minimize is a minimax objective, right? Minimax means minimize the maximum of a function. That's what minimax is. You first of all get the maximum, and then you get the minimum of the maximum, right? So so you take the log of the output from the um, discriminator, right? And then you get the maximum um, for a particular discriminator, and you get the minimum for the generator, right? And then you add that to the same function. This is kind of a cost function, right? That is the difference, right? So you use this log 1 minus d, what the discriminator generates, d g z. So gz is the generated value. D of gz is the discriminator's calculation, or it's basically it's 1 minus this, which is basically the difference between um um what the discriminator has detected as the difference between the two samples. That's what this is effectively. Okay, so that's GAN. And the way you train a GAN is the first step, you train a discriminator first. So like I say, you're training two neural networks, basically. That's why it takes much longer. So the first thing is you you give the real data, you give it a label of one, and then the fake data, you give it a label of zero. So you train the discriminator, right? When it identifies or when it thinks that the data you give to it is real, it will give you one. But when it thinks that the data you give to it is fake, it gives you zero, right? So you calculate the loss, which is whatever loss function you are using. You calculate the discriminator's, you know, label for the real value, right? And the real labels, okay, the real labels are all ones. So you calculate the loss function between that, okay? Then you now take the fake data, which is G of Z, where G is the generator, right? And then you now calculate the um the D is the discriminator. So you now calculate the discriminator. So what it thinks of the fake data, it could actually think it is one or zero. Of course, if it is one, that means the discriminator has failed. It basically is misclassifying the fake data. But if it thinks it's zero, then the discriminator is okay, right? So it's kind of think of it like similar to um, binary cross entropy that we're using for binary classification. Basically, you're saying it should be one if it is correct, and it should be zero if it is not correct, something like that. So in this case, it's calculating the loss from what the discriminator is able to think or to, whether it's able to distinguish the fake, whatever it thinks the fake is, right? So if the fake is zeros like fake labels, right? So if the fake is if it thinks the fake is real, then this loss will be higher. But if it thinks the fake is fake, then this loss will be lower. So you now have a situation where you're calculating the real loss, what it thinks of the real value and what it thinks of the fake value. And the total loss is the combined loss. So the discriminator is actually supposed to be able to, when it's real loss, it's supposed to predict one all the time. And when it is fake, from the generator, it's supposed to predict zero all the time. That is where these two losses will be zero and you have a zero loss. But if not, the loss will have some kind of value. And we'll now use that loss, right, to do back propagation, right? The DLoss that dot backward and then optimizer dot step, right? You do use that to train the discriminator. But when you're training the generator, you only train the generator on whether the discriminator was able to detect its own generated output, right? So essentially the G loss is the same thing as the fake loss, as you can see. So that's it. So effectively, you first of all train the discriminator maybe on one epoch, right, with this loss calculation. Then you train the generator on one epoch with this loss calculation. Then you go back again. You train discriminator again on one epoch, and then you train the generator on the next epoch, right? You just keep doing that. So you have to train discriminator first, then you train generator, then next epoch train. So this train we are talking about, you pull a lot of data. So it's also a loop which can last maybe like depending on how much data you're loading, your batch size and everything, that is already a loop. So you have two loops that are running side by side. I think we can actually try it, but I would rather try to train a diffusion model than trying to train a GAN. But I would say, okay, go try this out on your own, right? And see if you can train a GAN on image data and see if we can generate the image. But we'll see how we can do that with diffusion models. Okay, so these are some of the challenges with GANs. You have what we call the mode collapse. Training is always unstable. It fluctuates a lot, right? It's easy for you to have vanishing gradients. And the hyperparameters, if you adjust a little bit, is really very sensitive, right? So there were a bunch of improvements, including things like the WGAN, um, having a penalty for gradient, and then spectral normalization. But like I said, I'm not going to go into much details on the GANs. Instead, let's look at diffusion models. So a diffusion model is essentially a type of Gen AI. So this is a third type of Gen AI. And currently, the diffusion models are the ones that are most um, popular. They are like the state of the art when it comes to image generation models. These are the ones that are the best currently used. The best image generation models are diffusion models. And they essentially just create high quality data. Interestingly, diffusion models started off with creating image data, but they use them for every other thing now. So it can also create images and even videos. So when you see all of these models that are generating AI videos, right? Um, even music, sound, even when you hear things like voice mimicking or voice cloning, right? These are all diffusion models basically that are trained on that data. So you train on that data and it's able to generate, it's able to like we said, it will have some kind of understanding of the data distribution and it can generate samples of that data to a very high quality. So the way the diffusion model works is you have noising and denoising. It's two-step process, right? Um, so you first of all, um, it starts by um, learning to reverse a noise adding process, right? The noise adding process is what I call noising. So it starts off by taking a clean image or any data, sound, music, whatever. It takes that clean image and it introduces Gaussian noise, right? That's a forward diffusion process or forward propagation, right? Well, it's not really forward propagation, it's a forward training, the forward step of the training, right? So you destroy the training data with Gaussian noise, and then you train a neural network to reconstruct the original data by denoising it. So denoising is the model learns to remove the noise, right? Um, you know, the reverse process effectively. So the forward process, you take an image, you incrementally add noise over several steps, right? So you add noise small to the image. And when you say adding noise, remember images, by the time you are training, you have taken that image, you have converted it to just numbers, right? But those numbers have meaning because they're pixels, right? But when you start introducing noise to those numbers, introducing noise basically means adding some random numbers to the number, to the original numbers that represented those pixels. You now add some random numbers to it. As you're adding random numbers incrementally, of course, the image loses, what makes it the image, right? So it effectively becomes noise at the end of that first process, which is the noising process or the forward diffusion process. At that point, it basically becomes what we call Gaussian noise, right? Then you now reverse that noising process. You now have what we call denoising process. In this denoising process, you are training the model to reverse that process, right? So you are training it to remove the noise step by step to generate a new structured sample from random Gaussian noise. So the way you are training it is that as at each step, you will give it a less noisy image. Of course, you had the noisy image. You are the one that was adding noise to the image as in the forward step. So as you are reversing the step, you are giving it less and less noisy images, and it continues learning until eventually it learns how to denoise on its own. So unlike the GANs, which can suffer from mode collapse, right? Diffusion models will provide a more stable, diverse, and high fidelity output, right? And the beauty of it is that you can use it to create output from other forms, that is other medium or media, right? So you can actually use text and it will generate image based on that text, especially if you trained it that way, right? So I'm going to show a bit of example of how this is done, right? So I think we'll take a look at that. Maybe at the end of this, just look at the code. Okay, so right. So application of diffusion models, image generation, like we've said, you can actually create images from text prompts. So if you have ever wondered how was this, how was this done, right? They basically um, you know, um, you start off with text and then you give it images and then you noise the images, right? And then you train it to regenerate the images. So that's it. Um, then image inpainting and manipulation. So this is another interesting um, thing, right? You already have images. And you can modify um, the parts of it, right? Modify parts of the image by filling in, modifying. So you could take an image and, of somebody's face, adjust the nose, and it like you won't have any artifacts. Adjust the mouth, adjust the different parts. Those are the things you can do with diffusion models. Then increasing resolution of low quality images, right? Um, so this is also very, very, you know, interesting because what you are doing effectively is you are asking the model to kind of predict. Because what's happening with a low resolution or low quality image is that there's additional information that is missing effectively. So think of it like you are giving a text model a sentence, but the sentence is incomplete, or the sentence has dashes all over it, right? It has dash here, dash here, dash here. And it is able to fill in that because it is trained on data, it's able to predict what should be in the dashes. That's the same thing with what we call upscaling images. So when you have image that's very low quality, low resolution, essentially the pixels are inadequate. You have missing information between pixels. So when you upscale an image and you retain the original pixels, what's actually happening is that in between one pixel and the next, there is there are additional pixels that can range from one to whatever, right? But you don't know what those values of those pixels are between the two pixels because essentially upscaling is I take let's say 28 by 28 image like what we use with MNIST and I want to increase it or let's say 32 by 32 image, the cipher image, right? Cipher 10, and I want to upscale it. So I'm changing the resolution from 32 by 32 to 64 by 64, for example. I will retain all the original 32 pixels on each side, right? But that means that there is a gap in between each pixel. That's essentially what we are doing. We are now spacing it out. So there's a gap in between every two pixels that is missing information. We don't know what the value of that pixel should be. So since we have a model that we have trained, it can then extrapolate what that pixel in between should look like, right? What it should represent, what part of, you know. So it's kind of filling the blanks between pixels. And the better trained it is, the better it's able to fill in the blanks. So I could even upscale that image from 32 to maybe 64 or 128 by 28, 128, right? Or 256 by 256. So if I upscale it to 256 by 256, that's more or less like from 32 by 32. That's more or less like maybe four additional pixels in between, right? 32, 64, that's one. 128, that's four, right? Or three. 4, 128, 256 is 8, 512 is 16. So 15 pixels in between, right? And we have to extrapolate what those 15 pixels should contain. So diffusion model is able to do that by predicting the pixels in between effectively. That's essentially what it's doing. And for models that can generate from scratch, what stops it from doing that? All right. Then data synthesis is also another application where it generates realistic synthetic data for scientific applications. So these days, if you even want to do scientific experiments and things like that, or you want to try out methods, you can actually generate data based on, if you have a small data set, you can train your model on that small data set and it will generate more and more data that are similar to that small data set. And that means you have a larger data set for you to use for experiments. So the advantage of diffusion models, high quality and diversity, they produce more realistic and diverse images compared to previous methods. Stability, training process is more stable than the GANs, the generative adversarial networks. The disadvantage is that it is slow sampling, right? Due to the iterative step-by-step denoising process. So generating images can be slower than other models because you have to essentially do denoising step by step. So effectively, diffusion models are also learning the underlying structure of data, by learning how to denoise it. So this is the intuition behind it. You have a gradual noising process, right? So during the forward process, you have x0 to x1 to xt. So at each of these steps, right, you add a little bit more noise. So you can see the model becomes noisier and noisier and noisier. At this point, it is just Gaussian noise, right? So that's the diffusion process. That's the forward process. That's the um, noising process. Okay. Now, in the reverse process, okay, you now you're essentially training it on the steps that you created while you were noising, right? So the model should be able to predict the noise at each step, but you are training it backwards. You are training it with data from the last most noisy image backwards to the least noisy image. Okay. So it kind of learns to predict the noise at each step. And that's what you do. So um after some time, it's able to um do that on its own, right? To any random Gaussian noise. You give it random Gaussian noise and it applies what it learns and uses what it learned, essentially the noise. So the training objective here, the cost function is to calculate the epsilon here represents the noise, right? So epsilon is the current noise minus epsilon theta xt t. It's still kind of a mean square problem, right? And you are asking it to predict the noise that has been added. So that's we call it DDPM, denoising diffusion probabilistic model. So for each diffusion step, this is a chart that shows you how much noise is added, right? So depending on which sample you are using or the method you're using for adding noise, you could use square root, right? That's a green line. You could use a linear approach, or you can use a cosine, right? So so this is DDPM, right? You start with XT. Um, this is the forward. You start with um, this is the actual image, right? It's even having a little noise to it, right? But this is X0. Then you give it noise, right? And um, you now have in the forward step, you have Q XT given XT minus 1. And then P0 is the probability of the amount of noise between two steps, right? So we're going to look in more detail at that. So again, this is also another example, right? So you start with data that is clean image. You keep adding noise. After enough epochs, you've completely obfuscated the image, so it becomes Gaussian noise, right? And um, in the reverse, you are now calculating the amount of noise, right? It's able to calculate the amount of noise between each time step, right? Um, and it does that by essentially calculating the amount of noise in the final image during the noising process versus the amount of noise in the original image. So it's basically able to predict the amount of noise. And so reversing the process is when you start with a noisy image, right? It is able to predict the amount of noise that it needs to remove to move to the next step, and so on and so forth. So so what we are saying is that when you start from noisy, XT is the original, well, the finally fully noised image, right? In the forward step, right? And you start with that noisy image, which is represented by this function. This n basically represents a noise function. And then you iteratively denoise, right? By essentially calculating the amount of the value of the value of the input, right, in the previous time step as a function of the current time step, right? And then t being the time step itself. So this is what you are giving to it to be able to predict or learn. You train it on this. Again, I'm going to explain in more detail. Um, so I think we've talked about this. It's very stable. The image that you get out of it is very high quality. Disadvantage is that it is very slow generation. Um, okay. So this again is another example of the process. You start with a training image, you pass it through. During the forward diffusion process, you add a lot of noise. During the reverse diffusion process, you take that data, that noisy data across each step and use it to train the model. So the model is able to predict better. So stable diffusion is, I think, a bunch of researchers that came up with that, a very good method. So some of the key innovations of stable diffusion was, one, it operates in latent space, and then they do text conditioning via embeddings, right? So it is faster than this pixel space diffusion. Okay. So you can see how it is here. You have an image encoder, right? And then you have latent space, basically latent representation, because you have passed this image through an encoder. So there is a latent representation, and there's what they call a clip objective, right? Then they now have a text encoder as well, right? So this text encoder takes the correct, like, think of it like a training data that, you know, think of it like a label data for this caption, okay? So they take this, they pass it through a text encoder. So the text encoder also generates a latent representation of this text after being trained. And you see that with stable diffusion, actually using pre-trained models is better because it's going to be difficult for you to train an image encoder during this process. So it's better you take a pre-trained image encoder and then you take a pre-trained text encoder, right? So they already have latent representations. So what they now do is this image encoder has this latent representation, but this text also has a latent representation, and they are not the same, right? They are not the same, but you now have a way of correlating them, right? Learning the um, learning to map them, kind of, right, within the representational space, so that you can then take this same um, text representation and pass it to a decoder, right? But before passing it to a decoder, you have this model that you have trained, right, to be able to map the text representation of this, the latent space representation of the caption to the latent space representation of the image. So being able to train a model that maps the two, it is now able to generate this image. So all this model does is to be able to translate this representation from the latent space in the text to the latent space in the image, and then you pass it through a decoder. So a whole bunch of really um, you know um, um, clever innovations. So they have the pixel space. So this pixel space is basically latent space for the pixels, right? And then you have this text space, which is the latent space for the text, right? So and that's basically how Stable Diffusion were able to achieve using text to generate images, right? Um, this is kind of another more detailed representation of that, right? So you have pixel space, right? In pixel space, you have the original image, which is X. You pass it through encoder, right? You now have the Z, which is the internal representation, right, of the pixel in latent space. This is latent space. Then a diffusion process is used, right? And then you arrive at the ZT, which is you know, the latent representation after noising has been applied, right? Then you denoise it, right? But during this denoising process, okay, you now have encoder decoder attention, um, the attention encoder and decoder, right? So you pass the denoising through a transformer effectively, right? So you have the QKV, two layers of an encoder, right? And then QKV, two layers of a decoder. So effectively, what this does is think of it like a sequence-to-sequence model. It takes this ZT and it moves it, right, from this latent space into this ZT minus one, the previous latent space, but modulated by the text. And this text is also in latent space. The text comes from, um, you know, you do some text conditioning anyway. So you have semantic map, then you have the text, then you have the representations, and then you have images. So all of these texts go into another encoder here, right? Which takes the text and, it comes in here. So this text is actually going to modulate this. And by modulating it, it influences the each step-by-step denoising. Remember, denoising is step-by-step. So this is the first step from ZT to ZT minus one. So if you remember, I showed you this is the whole process. Noising, then denoising, you are training the model to regenerate the image by removing the noise. But this time around, we modulate it by the text that comes in. So each step is modulated by this, right? And we are using cross attention basically. So cross attention, um, you take in cross attention, the Q will come from the image side, right? While the KV comes from the text, right? So the interesting thing is that all of this thing is happening in latent space. In other words, it's after the first um, you know conversion from the image or pixel space into the latent space, or from the word, sequence embedding or sequence space into the latent space. Okay. So you can look at this. You see that the first thing is that you have a concat here. So in this concat, we are taking the latent representation basically of the word of this the sequence of words, and you pass it into this to concat, right? By the way, this is a switch. So switch is to switch between two different states when you are training and when you are doing inference, right? So it goes here, and this is the first part of it, but you can also do cross attention here, which is what this is, basically cross attention. So remember we said how cross attention, you can use it to bring um the internal representation basically from the encoder, you bring it to influence what the decoder does. So essentially they used the same principle right here. So this is kind of cross attention, right? And except that it's now cross attention, encoder, decoder, it comes out. And you have another one here. So this is basically the same thing as this, right? It's just that they don't need to repeat it. It's smaller. So after each step, you do this. After each step, you do this. So effectively, the latent meaning or the meaning of the string that you typed in as a prompt begins to affect the step-by-step denoising of the image, right, in the latent space. And you end up with an image X, right, which should match the original image. Of course, training now happens, right? So in training, you are training it with an image, right, X, and then you are giving it the semantic strings, and you do your loss function. All of this goes through back propagation. It's end to end, right? So at the end of the day, you end up with a model that is trained to generate images from prompts. So in case this is kind of a bit high level, I think I may want to I'll share a video of how this is done, but I will also kind of show you like a notebook where you can use this. I'll share a notebook where you can use this. So this is still the same thing, except that this time around you have additionally the algorithms that are used for training the models. So these are now like a bit more advanced, and I'm not going to jump into this um, just yet. This is kind of what we'll be doing in the intermediate class, where we'll break these things down and actually begin to train our own models. But these are really advanced stuff. So at the end of the day, this is stable diffusion, right? Input, this is basically a summary of what we've just discussed. Input comes in, you have a diffusion model, output, right? Then this was where it all started. Now, input, you now have an encoder in the latent space, right? After input has generated, you now have the encoder, right? You have an encoder first that generates in the latent space. You now put the diffusion model in the latent space, and then you have a decoder, right? So that is stable diffusion. But now in that latent space, you now have cross attention, right? From an external, um, you know, model, the the text model, the language model that will encode whatever string or a sequence of words that you have. It encodes it into latent space, and that is used to modulate the process, right? Via cross attention. And that's stable diffusion. So let's just round up with representation learning. So at the end of the day, right, all generative models will learn what we call the latent representation. Okay. So for autoencoders, we have compression mapping, that's the latent representation. For variational autoencoders, it's a structured probabilistic space. For GANs, generative adversarial networks, it is an implicit manifold mapping, right? For diffusion models, it's a noise to data trajectory. So these are all latent internal representations of the data that you are training it or you have trained it on. Okay. So when you are in latent space, right, because the representation of data has been compressed and kind of normalized in the sense that they all different things. It's now in representation space or in latent space. Representation now boils down to meaning, right? It is no more about the semantics or the syntax or the language, right? The word boy could mean the same thing as garçon, which is a French for boy, right? But in those are two different words outside, but in the latent space, those might actually map to the same thing, to the same point. So in latent space, we're now dealing with normalized meaning. Basically, everything in latent space is meaning, right? So you can now begin to manipulate stuff in that latent space. So that now allows us those manipulations to do things like interpolation. When you interpolate between two things in the latent space, right? Style transfer, where you can take the meaning of, in one dimension, which can represent style in the latent space and apply that value to something else in the latent space, you now change the style of it, right? Again, these are kind of advanced stuff which we cannot touch on them for lack of time. Conditional generation, data augmentation, right? So that's what it is. And you can see that the different models that or methods that you can use for generative modeling. If you want to do reconstruction based, you use autoencoders. If you want to use variational inference, use the variational autoencoders. If you want to do optimization based on game theory, why they're saying game theory is because you are actually putting two models to fight against each other, to battle against each other. So it's kind of game theoretic optimization. It's optimization using a game theory approach where you have adversarial networks that are battling each other to see who can outwit each other, right? Who can outwit the other rather. So that's a GAN. And then Markov chain denoising, right, is a diffusion model. So we can talk about Markov chains later. So, but the interesting thing is at the end of the day, these are different approaches, different philosophies, but ultimately the same goal is to learn the probabilistic distribution, right, in that data, right, which it can then use to generate other data. And that's essentially what we mean by representational learning. Okay, so um, at the end of the day, we can compare these different methods, right? Um, Variational autoencoders have high stability in training. Sample quality is moderate. Speed is fast, right? GANs are training stability is medium. Sample quality is sharp. Speed is also fast. Diffusion models training stability is very high. Is the state of the art in terms of the quality of what they can generate. That's why you see recent images. You can go compare any of these two to see images they generate or videos. It's really the diffusion models that are used to generate videos that give us really high quality. But the speed is slow because you are training across each of the steps, the denoising steps, right? So, and that's it. Principle of operation, autoencoders learn the compressed representation. Variational autoencoders now take that compressed representation they have learned and they use a distributed approach, right, to learn the structured distribution of in the latent space. GANs use adversarial training and sharp outputs. Diffusion basically is reversal of the noising process, right? And it's the most stable and highest quality. So that brings us to the end of generative models. Are there any questions? No questions. That's a lot of theory, right? So I'm going to share a quick notebook that I did. There are two things that I'd love to do, but we're out of time, so I'm just going to quickly share the notebook on let me find the notebook. I have a notebook for retraining. I think we may have to do just one more session, right? But then again, I can just share the notebook so you can go study it. Um, so the idea is, um, I talked about large language models earlier and how you can train large language models, fine-tune them, basically fine-tuning large language transformer models. So let me show you this. So now using PyTorch is not really the best approach, right? Um, for this because using PyTorch is going to be challenging. Um, PyTorch is a framework, it's powerful, but at the level that we are with training models today, it's still there are now approaches and tools that kind of even help more with a lot of things. So we are going to have a session next week, maybe just one session, where we are going to look at um the how we can fine tune models, pre-trained models. But these are the steps. So the first thing is that you have to choose a pre-trained model. And you can decide which ones you want to start with, right? Depending on the particular problem you want to solve. So for text classification, you can go to Hugging Face. So the first thing is we go to Hugging Face. So we don't have to start from scratch. Hugging Face has a lot of models, right? And not only do they have a lot of models, they have data sets as well that you can pull. And these are all open source. A lot of different companies, research institutions, startups that contribute. They contribute data, they contribute models, right? So you see all of these large language models here as well. Spaces is a place where you can share, things with a close group of people if you don't want to share it to the whole world. They have that and they have community and then they have docs. So there's a lot that you can get in Hugging Face. Um, so the first thing is you can go look for pre-trained models, right? So depending on the task you want to do, like if you want to do text classification, then you're looking for an encoder model. Remember, encoders give you an internal representation, while decoders give you a sequence or they output a sequence basically from the internal representation. That's one thing you need to understand. So if you want to do classification, you need an internal representation. And there are two that are recommended here. You can use the BERT based on case, and then you have the steel BERT based on case. You can actually look for these models here. Just search for it here. And let's see if we still have them here. So these are you can see this Google. So this is the BERT model like we talked about earlier. It's a pre-trained model on English language, right? And it uses matched language modeling. So like, remember we talked about it already, where you are masking some of the words that you send to train it. So it learns how to predict words. It's bidirectional. You're not masking only future words. You're masking everywhere. Okay. So of course, this is the paper that they did. So this is a kind of bet, right? This model is on case, meaning it does not differentiate between lowercase and uppercase. That's what that means. So when you hear base, bed base uncased. So you get this model, you can just go check out there are different sizes, different parameter sizes. So this base is 110 million parameter. These are small models. You can easily run in a Jupyter notebook, right? Compared to the current models that are billions, right? Uh, then you have large 340, and those are the only two sizes you have basically. There's also a multilingual, right? So if you want to train on your own language, it's best to start with a multilingual because it's been trained on different languages. So it understands internal representation of different languages, not just of one language. So this is more suited. For example, if you wanted to train a model to translate your own native language to English or to any other language, you would start off with this, right? It will make it easier for you. You start off with bed-based multilingual, for example. But this is if you want to teach it some kind of domain-specific thing. So for me, I would even have loved to do this language thing if I had more time, but maybe we can try that next week. Um, then, so you start with that, right? Um, and then if you want to do a QA thing, depending on the problem, right? QA is question and answer, so like a chatbot kind of thing. Then you can use this one. This one is whole word masking, right? Fine-tuned. Then this is kind of um, you have a specific one for NER, right? So we can check let's check that one out. Maybe I can even just copy it. Distilled bread. Let me search for this. Um, let's see if this gets us there. Okay, it's not there anymore. Let me search for birds there. Okay, so it looks like it redirects to something else. Redirects to something else. Um, so yeah, that's probably not there anymore. Okay, so that's the first step. You choose a pre-trained model. Then the second thing is you choose data sets you want to use to train. So if you want to train a model to do classification, you can use IMDb, right? And then you have the classification thing there, right? If you want to train the model to do maybe translate your language, then you have to have a data set that contains labeled, versions of your language and so on. So I think we could do that as a project. That would be a nice project to do. Okay, so then you load the data set. So like in this case, we want to do there's a task where we're saying do sentiment classification IMDb. But in that case, we are training model from scratch, right? But here you would do much better if you basically have oh, by the way, let me see what I am using. I'm currently using oh yeah, let me see. I am using a CPU. Let me make sure that I shouldn't have any sessions except this one. Yeah. Okay. So right now, it's downloaded. Okay. So if you also have a custom data set, you can configure it and do that here as well. But I don't have a custom data set, so I'm just going to use IMDb for now. Then you need transformers. Transformers are the Hugging Face basically the library that gives you additional capabilities on top of PyTorch. So Transformers is built on top of PyTorch. You would have to install Transformers datasets and evaluate. We've done this before already. I think okay, when you use sentence transformers, for example. So Transformers, right? Then of course you import it. So we will import um yeah, we can import these. So let me make this shorter. So we can import auto tokenizer, that trainer. So trainer is a very useful class that Hugging Face provides that basically handles training for you. So you don't have to work too hard, right? And sometimes you don't need to write the entire training loop. So we import all of those. Then, of course, you have to tokenize. You have to tokenize. So we use the DistillBet for tokenization. Let's see what I got here. Okay, well, we use DistillBet. So when you have the auto tokenizer class, so we don't need to work too hard to do tokenization. If you remember when we're doing tokenization, we had to write code that would split based on species and all of that. But Hugging Face has an auto tokenizer which does that. It essentially uses a model to do the tokenization. So when you use from pre-trained, you're basically saying, use this pre-trained model and use it for my tokenizer. Okay, so that's what we are doing now. So of course, Dilbert base was not downloaded, so it's downloaded it now, right? It has to download a bunch of other things as well. Um, all right. So now in you have a preprocess function. In the preprocess function, which is what you're going to put through into your batch, into your data pipeline, basically, you will return a tokenizer. The tokenizer is actually going to run tokenization on the text, right? Truncation is true, padding is true, right? So this is like standard stuff. Truncation is essentially useful so that you don't have sequence lengths that are too long. Okay. So so now we now run the data set. So remember we've downloaded the data set already from the IMDb, right? So by the way, I think I should switch this to a GPU. So let me switch this to um yeah, let me use an A100. So hopefully to be a bit faster. I've not tried a H100 before. Maybe this is a time to try one. H100 should be faster. It's going to burn a bunch of my it's going to burn a bunch of my units, but that's okay. All right, so we'll have to start again. It's trying to connect. I hope we can get a H100. H100s are probably going to be very difficult to get because of how they are really fast. So a lot of people will want to use it for their training. But if I can't get a H100, I'll try an A100. If I can, then I'll go for the T4. Okay, so this is basically now putting our essentially we take our data set, we run it through the tokenization. So we now have a data set that is encoded, basically tokenized. I think the tokenizer also does embeddings as well. So we can actually look at what is in it. So yeah, so you can see I couldn't get the GPU I wanted, right? So they gave me a G4. Um, I couldn't get a H100, so they gave me a G4. Well, that's okay. I don't know if a G4 is better than an A. I don't know if it's better than an A100. Yeah, I guess it's better. So let's go. All right. So yeah, we'll get the data set. I did not specify Hugging Face token, but it still downloads it nevertheless because it's a public free data set, right? Um, okay. And now I'll skip this custom data set basically. And then I will again run this. This is a new runtime, so it's basically a new server. Um, okay. So all of this has been installed. So I'm going to import as well. Then we'll now run auto tokenizer from pre-trained. So yeah, with this, I have a tokenizer. Then the pre-process, so I can look at my data set. Let's look at data set before we map it, right? So we can just run maybe the first 10 rows in the data set. Um, okay, so I need to select a split before I can slice. So test, or let's do train. Okay. All right. So the first 10, um, this is just the first 10, and this is a lot. So let me just take the first one, right? So this is the first. So you can see it's text, right? So you have text. You have text, you also have label. I could have printed it. So each oh yeah, so this is not very nice. I could do JSON dot, but let me not go to all of that. So this is it. You can see there is a text, right? So this is the text. All of this is just entire text, just a single data point that we'll use to train. And then the label is 0. So remember, this is a sentiment, this IMDb sentiment classification database. So in the sentiment classification database, the labels, there are only two values for the labels. Um, if the label is 1, right, it means good, right? It means true, good. If the label is 0, it means bad. So you can see in this case, you can see that this is a negative criticism of the movie. So the label is 0, meaning that it's negative, right? Okay, so that's the data. Now we encode the data, right? If we after we encode the data, you can go back and check at our map. Our map is taking the text, right? The text this thing from that batch, right? And tokenizing it, right? But what I want to check is whether it does embedding as well. So after running the encoded data set, you can see it's taking a bunch of time. But yeah, this uses GPU, so you can see it's a bit fast. Now, after this is done, I would now want to also print data set. Yeah, so now I want to see what it looks like after encoding. So you can see this is encoding based on it's encoding, it's not just tokenizing it, it's encoding it. So you can see attention mask, it has a whole bunch of stuff here, the attention mask and the actual values. So this is a lot, token type IDs. You can see the number of, yeah, so these are the IDs, the indices into the vocabulary. So yeah, so you can see the indices. So that's the input IDs basically. And this is the original text. So it still retains the original text and the label, but it now gives you the encoded IDs 101045 for each of the words. So 101, for example, represents is the index for I in the vocabulary. 1045 is the index for rented, and so on. 12524 is well, I'm surprised that I is also having a different number, but remember that okay, I assume 1015 is I, right? Then 12524 is rented. Then I again is 1045, right? Is 2572 and so on. So this 101 might have been a pad for the starting index. So anyway, yeah, so this is what you get from the encoded data set. Right. So now let's look at training. So remember, we are fine-tuning a pre-trained model. So we are not starting from scratch. We'll get the model by using this Hugging Face function, the auto model for sequence classification. If you check, I actually imported it here from transformers. So auto model for sequence classification. So we already have a model that has been set up, a class has already been set up to do that, right? And from pre-trained, so we are taking it from the deal bet. Okay. So we have a bunch of unexpected missing, right? Unexpected can be ignored when loading from different tasks, not okay if you expect identifier architecture. Those params were newly initialized because missing from the checkpoint. So effectively, we are pulling it from a checkpoint, but there are some parameters that are missing, right? I am assuming that this will not affect training so much, so we'll just ignore it for now. Right. So we also imported the training arguments, right? So this allows us to set up training easily. So you can see we have a training argument. So you specify where you want to store your training. So that will be a directory here called results. Evaluation strategy is epoch. So we want to evaluate every epoch, right? That so many different values you can try here. Learning rate, you specify the, so these are basically training parameters and other arguments. So we are using a 2 raised to power minus 5. So that's 0.0002. And the reason why this learning rate is so low is because you are fine tuning. So you don't normally use a very high learning rate, because if you use a high learning rate, you are basically going to destroy the base model, right? So you use a small learning rate. Then you have a per device train batch size. So this is batch size. If you have multiple devices, then this batch size, so this is for each device. Essentially, device is each GPU, okay? For training, and then for eval, 16. The number of epochs, we want to train 3 epochs. Weight decay, this is regularization, L2 regularization. Then we have a log directory. So these are the parameters, right? Okay, so I think there is some, let's see, output directory. So it's changed to eval strategy. Let's see, output directory, um, learning rate, right, per device train. You have a whole lot of parameters. It's huge. They even have TQGM and all of that. So let me try this again. Okay, so it was eval strategy. All right. So there's also another deprecated this, which, so we can use TensorBoard for logging, but that will still work for us. So this sets up our training parameters, and then we now use a trainer. So you can see with a trainer, we don't need to do all of that training loop ourselves anymore. We just set up all the training parameters, okay? And then we call trainer. Trainer will do the training. That whole loop of, you know, go to training mode, do inference, forward propagation, forward pass, calculate cost, calculate loss, back propagate, update weight, and even do a val, right? Calculate, the losses against the tests data set and so on. So all of this, right, is handled here. And you even specify the training data set, which is encoded data set train. And you also specify the test data set, which in this case, they call it eval data set. And then you pass in the training arguments, you pass in the model. So remember, this model is the model that we had already pulled from a pre-trained model, right? So we are ready. We set up the trainer and we just call trainer train, right? That's it. So Hugging Face makes it really easy using the trainer class, right? It helps you when you're now trying to do really advanced stuff, because all of the potential error that you may make, especially in running the training loop, right? They've handled all of that. The only thing you now have to focus on is, did I pick the right hyperparameters, learning rate, weight decay? Did I pick the right model, pre-trained model? Did I pick the right data set? Am I doing the right data processing, cleaning, you know, um, um, you know, whatever transformations that you want to do on the data, So you just focus on the things that are that's specific to your training, not the things that are always like repetitive. All this while we have been doing our own training loops. And I left that deliberately because it is important for us to um understand how those things work, right? The same way we started off with linear regression, logistic regression, it gives you solid foundation. So we know, so it's not like when you come and see trainer and then you say trainer.train, you think that it's easy. It's not easy. There's a lot of code behind this, but at least now you have written your code, so you know what it is. And yeah, it's good that I used a really fast GPU for this, right? This is hopefully in the next you know maybe in 3 minutes it should be done, I assume. It's really fast. So All right. So when that is done, then we can evaluate, right? We can evaluate and then we can save the pre-trained model, right? The good thing is you can save the model here and then download it from here and keep it in your local, system so that you can further train it. So one of the things that if you are using Colab, like Colab Pro, like I said last time, you can go purchase a few units and do some of your training. If you save your model here, it is going to get lost once that runtime, because this file, this any data here is actually in a runtime that is, transient. It will be taken down by Google, right? If you don't use it for a while. Okay. In fact, even if you use it for a while, after some time, rate limiting, they may still take it down. So if you have invested a lot of your units and time training models, please don't just store them here. There is a way you can send the model directly into your Google Drive. I'm going to show you how to do that, right? So, but alternatively, you can save it and download, but downloading is not really good because you're essentially going to download into your computer and then you have to upload it again and all of that. So sometimes for very large models, that may be unnecessary waste of your bandwidth and data. So one way you can do this is effectively or essentially just push it straight into your Google Drive, right? And once you push it to your Google Drive, you can pull it back down. Um, yeah. So that's it basically. After that you can save, and then if you want to load it later, yeah. So save pre-train is going to save it in here. If you want to load it later, you still use a pipeline, right? And you can um, you know, use this to pull it, and then you run the classifier. So classifier is just a way of pulling your stuff in, right? And then you can run it. Yeah. So let me show you how you can store this in a drive. Um, One of the ways to do this is to use mount, drive.mount. So let me show you this. Um, Storing your model in Google Drive. So first thing is, yeah, the first thing is you have to basically there is drive, right? So you use drive, then you mount the drive. So when you mount the drive, this is actually your Google Drive that you're mounting. Okay. Now when you run this, it's going to ask you to sign into the account and grant permission. I think that's the best way here because it ensures that people don't have access to your drive, because that's one thing you have to be careful about, right? So after mounting it, um, yeah, after mounting it, let me put this here so that after you mount, then you can just easily upload anything that you want to upload, right? It will allow you to easily upload anything you want to upload. You just call that mounted drive location. So that's it's very, very simple to do. And it also helps you. So yeah, so this is how you save it. This is how you save it. This is the code. So you have the save path. You specify the path here, right? So you have content drive, my drive, right? Then you just save the model. You just save, assuming you already have the model, the train model here. And then you see it there. Um, Let me see the format that is used. Okay, so this train is done. So you can see, um,
it has trained 3 epochs, right? It gives you some of the metrics, right? Train samples per second, train steps, total loss. You can now run evaluate on this. So if you run evaluate on this, um, it's basically running, this is 1563 is the size of the training data. I think I could actually check that by um, just length of um, um, data set, right? Test. So this is going to give us the size of the training data set. So the sorry, the test data set, right? Okay, this is 25,000. So, but we are doing evaluation on 1563. So you see, eval loss is 0.27. Eval runtime is this. Samples per second, steps per second. Okay. Um, all right. So we can save this model here. Okay. You can also save the tokenizer as well. Um, so let's run that. You see, they are saved here. All right. So this is the folder. This is a folder name. So it's going to create this folder name. And you can see it has saved the tokenizer. I could open this and you see um, it gives you all the information on the tokenizer. Right. So you have all of these slots that are unused, but down here you see the vocabulary basically that the tokenizer has, and you see some of these interesting characters. You also notice that these are not tokenizing by words anymore, right? It has a bunch of other things as well. So yeah, these are, you know, LLM based or neural network based tokenizers. So you still see sometimes it does stuff like this. But yes, yeah. So that's your tokenizer with vocabulary. You can check the tokenizer config as well, right? Which was used to create. And then you can um this is your config for the model itself. And then these are the safe tensors. This is the model which this is a big file, so probably shouldn't have tried to open it. It's a big file. So anyway, so that's that. Um, now if we want to now later on load it, we can still load it, specify this model name, which is in this folder, right? We use transformer pipeline. We load it, and then we just, the classifier basically is the full pipeline. So, and we specify what type of pipeline. So a pipeline in Hugging Face is basically a full chain of everything, including the tokenizer, the model that will do the inference, and then the one that will decode the um, output from the model and give you the right values meaningful to you. So it's a whole pipeline, and this particular pipeline is a named pipeline for text classification. So this basically will load the model, and when you now pass in your inputs that you want to do inference, this input is going to automatically get tokenized because the pipeline includes the tokenizer, right, and does all the other things. So you can now see that um, it loads the weights, it does this and it gives you a level and level score. And you can see level score is 0.99. So this is close to 1, meaning it was a positive, the sentiment is positive, was a positive thing. But if I now do classifier, right, and I say this movie was terrible, you now see this will give us a score that's close to 0. Oh, well, okay, I'm surprised. Its level is 0. Okay. So here's the thing. I think the score is a measure of the confidence in its prediction. The level is 1, meaning level 1. So it's a positive sentiment. and the score is 0.99. So it's 0.995%, 99.5% confidence that it is a positive one. While this one, the label is label 0, meaning it is a negative sentiment. And the score again is also 99.2% sure that this was a negative. So if I now do something that is somewhere in between, this movie was not too okay, but I, I, um, well, I still liked a few parts. I'm just trying to be ambiguous, right? So, this one runs. You can see it's still giving a level 1 score. That is positive, but it's less confidence. See, the confidence level has dropped, meaning I wasn't, it still notes that I still like a few parts. Okay. Um, I still wouldn't, um, I wouldn't watch it again, right? Okay. So if I say I wouldn't watch it again, then I wouldn't watch it again. It will likely give you a 0, and it's a very high score. So that's it. Now if I want to store it on Google Drive, I can run this. Okay. So here you now see this pop-up that says it should connect to Google Drive. So this allows you to make sure that you are the one that really wants to do it. It's going to even bring up your this whole thing for you to log into Google and continue. And you can give it access. I don't know if I want to give everything. Um, um, let's see. Create and delete, no. View photos, retrieve mobile client, view Google people, view the activity record files, see, edit, create, and delete any of your Google Drive documents, all of your Google Drive files. I don't really know what to do here, but I definitely don't like the idea of giving it everything, but let's see if that allows it to work. So it takes a bit of time. All right, so we can now do model save. Before we were doing model self save pre-trained. So we can still do the same thing, all right? The only difference is that here it is saving it directly into this folder. But here I can specify the path, right? I think I can still specify the whole path and use save pre-trained. So we'll still use save pre-trained. And this time around, we'll give it the full path, right? It's going to save into a folder. So um, let's run this. So it's saving this into my drive. So the interesting thing is I can open my drive and I should be able to see it. Let me open just to show you. Right. So you will see this here that okay. So you see this here. I think I somehow dropped it in the, let me separate this. So you see that, yeah, there is my drive. So you can see it has saved the model. It has saved the config.json, and it has also saved the save tensors. So it is now, right there. You can see the configuration. So this is the best way to save it, so that you don't lose it, right? Save pre-trained, you specify the full path. The path looks something like this, and that's it, right? So if I want to load again, the same thing, right? The same thing I did here where I said um, um, pipeline model equals this, right? You pass this, the full path to the model into this, okay? And it's going to load, from there. So that way you don't lose your trained model. Even for some reason, if you lose this runtime. So That's it. Down here, you have the whole thing put together. So a few things to just check out here. Um, you can see you use very low learning rate when you are fine tuning because you don't really want to mess up the base model, right? And then batch size, you can make larger batch size depending on GPU memory. Also, if you do too much of epochs, remember this is already a pre-trained model, so it already has a lot of latent knowledge in its latent space. So you don't need to train too much, right? It will overfit. And then you can apply evaluation metrics, FC, F1 and so on. If you want larger models, you can go check out. So basically, right, you can go to Hugging Face and pull any pre-trained model. And so that's kind of a a little introduction into fine tuning. I hope we'll try it. You'll find that one of the biggest challenges that you have is gathering the data. Gathering the data is always the difficult challenge. So I'm saying this so that one of the capstone projects will include fine-tuning a pre-trained model on something. So you get to know. It's good to have this skill. So I'll advise you go and try it out and try different models, try different ways. I'm going to share this notebook with everyone. So that's it. I hope we enjoyed the session.